Find somewhere comfortable tonight. Wherever you are, your bed, your couch, somewhere quiet in the dark. Just settle into it. You don't need to follow any of this closely. You don't need to hold on to the details or remember the names or keep track of where we are in the story. The words will arrive and you can let them pass through you like light through water, gently, without effort. We are going to spend some time with one of the deepest mysteries in all of science. Not to solve it. Nobody has. But to sit with it together. To let its vastness do what vastness does, which is to make the small things feel smaller and the quiet feel quieter and the present moment feel somehow like enough. The universe is expanding tonight. Right now, as you lie there, the fabric of space itself is stretching outward in every direction, carrying galaxies away from each other across distances so enormous that the numbers lose all meaning before they arrive, and something is pushing it. Something that fills all of space, that has no weight, no color, no detectable presence at all, and yet makes up more than 2/3 of everything that exists. Scientists call it dark energy. And they are the first to admit that they do not truly know what it is. That mystery is where we are headed, slowly. We are in no hurry tonight. If today was hard, if you carried something heavy through it, if your mind has been going in circles, if rest feels further away than it should, then let this be a place to set all of that down for a while. Not because the universe will fix anything, but because sometimes the most restful thing is to think about something so vast and so old and so far beyond our daily concerns that everything else, just for a moment, goes quiet. So let your body be heavy, let your eyes stay closed. And let's begin somewhere very specific. In the late 1990s, in the dim glow of a computer screen, where a group of astronomers were staring at numbers that could not possibly be right. The question they were trying to answer seemed, at first, like a simple one. How fast is the universe slowing down? Not whether it was slowing. That was assumed. The universe had been expanding since the Big Bang. Edwin Hubble had established that much back in 1929, and the evidence had only grown more solid in the decades since. Space was stretching. Galaxies were moving apart, but gravity, the great gathering force, was supposed to be applying a brake. All that matter spread across the cosmos, each particle pulling on every other particle across the void. It had to be adding up to something. The expansion, everyone agreed, must be decelerating. The only open question was by how much and what that rate of slowing would eventually mean for the universe's future. By the mid-1990s, 2 independent teams of astronomers had decided to measure it properly. They would do it by looking at supernovae, specific, particular kinds of stellar explosions, so far away that their light had been traveling for billions of years before reaching us. In those ancient signals, they hoped to read the universe's history, how fast it had been expanding long ago compared to how fast it was expanding now. The difference would tell them the deceleration rate, clean in principle, enormously difficult in practice. The first team was the Supernova Cosmology Project, based at Lawrence Berkeley National Laboratory in California, led by a physicist named Saul Perlmutter. Perlmutter had been working on this problem since the late 1980s, building the infrastructure, the software, the search strategies, the observing schedules needed to find and measure these distant explosions reliably. Supernova hunting is not a passive exercise. You cannot simply point a telescope at the sky and wait. You have to survey vast patches of sky, compare images taken weeks apart, identify the faint new pinpricks of light that weren't there before, and then race to capture their spectra, their chemical fingerprints. Perlmutter's team had spent years refining this process into something that could be done systematically, at scale. The second team was the High Z Supernova Search Team. High Z meaning they were looking for supernovae at high redshift, which is to say, very far away, very deep in time. This group was co-led by Brian Schmidt, an American-born astronomer working in Australia at the Mount Stromlo Observatory, and Adam Rees, a young researcher then at Harvard. The two teams knew about each other. They were, in the most collegial and professionally respectful sense of the word, rivals. They were racing to the same answer. The particular kind of supernova they were both hunting has a name, a Type Ia supernova, and the reason astronomers care so deeply about this specific variety comes down to a beautiful piece of physics. To understand it, picture a white dwarf, the dense, cooling remnant of a star that has burned through all its fuel and collapsed down to roughly the size of Earth, but with the mass of the sun packed inside it. A white dwarf sitting alone in space is stable, inert. It simply cools over billions of years like an ember. But many white dwarfs are not alone. They orbit a companion star, and in some binary systems, the white dwarf is close enough that it gradually pulls hydrogen from its partner, drawing it across the void between them and piling it onto its own surface. Here is where the physics becomes remarkable. A white dwarf can only accumulate so much extra mass before something gives way. There is a limit. Physicists call it the Chandrasekhar limit, after the astrophysicist Subrahmanyan Chandrasekhar, who calculated it in the 1930s, of approximately 1.5 times the mass of our Sun. When a white dwarf approaches that threshold, the carbon and oxygen at its core can no longer resist the pressure bearing down on them. A runaway nuclear fusion reaction ignites, carbon fusing into heavier elements, releasing an enormous wave of energy, and the entire star detonates in a single catastrophic explosion. Every atom blown outward, nothing left behind. What makes this so useful to astronomers is the consistency. Because the explosion always happens at essentially the same mass threshold, it always releases approximately the same amount of energy. Every Type Ia supernova, wherever it occurs in the universe, has very nearly the same intrinsic brightness at its peak. They are what astronomers call standard candles, objects whose true luminosity is known, so that their observed brightness tells you how far away they are. If a Type Ia supernova appears dim, it is not dim because it was a weak explosion. It is dim because it is distant. And by measuring exactly how dim, you can calculate exactly how distant. Both teams were measuring these supernovae at extreme distances, objects so far away that their light had left them when the universe was less than half its current age, and the method for determining distance was coupled with another measurement, redshift. As the universe expands, space itself stretches, and the light traveling through that space gets stretched along with it. A wavelength of light that began its journey as blue or green arrives at our telescopes shifted toward the red end of the spectrum, longer, lower in energy. The amount of that shift tells you how much the universe has expanded during the light's journey. Pair the redshift with the brightness, derived distance, and you have, in effect, a data point on a graph, the universe's expansion rate at a specific moment in cosmic history. Accumulate enough of those data points, stretching back far enough in time, and the graph tells you whether the universe was expanding faster in the past and has since slowed, which is what everyone expected to see, or whether something else entirely was happening. In 1997 and 1998, both teams were deep in their data. The numbers were coming in, and the numbers were wrong. Not wrong in the sense of measurement error, not wrong in the sense of a miscalibrated instrument or a contaminated sample, wrong in the sense that the universe was not behaving the way it was supposed to. The distant supernovae were fainter than the models predicted, not dramatically fainter, not fainter in a way that screamed out from the data, not fainter in a way that screamed out from the data, but fainter in a consistent, systematic way that could not be explained by dust or by some unusual population of white dwarfs or by any of the other alternative explanations the teams methodically worked through, one by one, over months. Fainter meant farther, and farther meant the universe had expanded more than expected between when that light was emitted and now, which meant the expansion had been slower in the past and was faster now, which meant the universe was not decelerating. It was accelerating. The expansion of space was speeding up. Adam Rees was the first to run the formal statistical analysis for the High Z team in late 1997. He described the moment of seeing the result clearly as one of the strangest of his scientific life. Not triumphant, but deeply unsettling. He checked his work. He checked it again. He sent it to colleagues, asking them to find the mistake. There was no mistake. Perlmutter's team arrived at the same conclusion independently, working through their own larger dataset. Two teams, different telescopes, different software, different members, different hemispheres, both arriving at the same result that neither had been looking for and neither wanted to believe. Both papers were submitted in early 1998. The results were announced, and a cosmologist at the University of Chicago named Michael Turner reached for a new word to describe the unknown thing that must be responsible. He called it dark energy, not because anyone knew what it was, but because something had to be named, and the name needed to carry the weight of the mystery. Dark, because it is invisible and undetected by any instrument we have ever built. Energy, because whatever it is pushing space apart with a force that is winning against the gravity of everything in the observable universe. The data had refused to be argued with. The universe was accelerating, and nothing in the existing framework of physics could explain why. To understand dark energy properly, or at least to understand the shape of the mystery as clearly as possible, you have to go back to 1915 and to a set of equations that changed what human beings understood about the nature of reality. Albert Einstein, in the final weeks of that year, completed his general theory of relativity. It was, and remains, one of the most profound achievements in the history of science. What it did, at its core, was rewrite the meaning of gravity. Newton had described gravity as a force, an invisible pull acting at a distance, drawing masses toward each other. Einstein replaced that picture with something geometrically richer and stranger. Gravity, in his description, is not a force at all. It is the curvature of space and time caused by the presence of mass and energy. Matter tells space how to curve. Curved space tells matter how to move. The two are inseparable, each shaping the other in a continuous, dynamic conversation. Picture space, not as an empty backdrop, but as something more like a fabric, though that analogy only goes so far. Place a heavy object on that fabric, and it creates a depression, a curve. A smaller object moving nearby follows that curve, tracing what feels like a circular path, and we call that orbit. What we experience as the pull of gravity is, in this picture, simply the tendency of objects to follow the straightest possible path through curved space. Einstein's equations, a set of relationships between the geometry of space-time and the distribution of energy and matter within it, were extraordinarily successful from the moment they appeared. They predicted the bending of light around the sun, confirmed during a solar eclipse in 1909. They predicted the precise rate at which Mercury's orbit slowly rotates, something Newton's gravity had never fully accounted for. They would go on to predict black holes, gravitational waves, and the expansion of the universe itself, though that last prediction made Einstein uncomfortable in a way that led to the very thing we are interested in tonight. When Einstein applied his equations to the universe as a whole in 1917, they did not produce a static cosmos. They produced a dynamic one. The geometry of space, filled with matter, could not sit still. The equations said the universe should either be expanding or contracting. This troubled Einstein deeply because the universe was understood, at that time, to be eternal and unchanging. The stars were simply there, as they had always been. The idea of a universe that was doing something, growing or shrinking, seemed almost philosophically improper. So Einstein introduced a correction. He added an extra term to his equations, a mathematical constant that he placed there deliberately to counteract the tendency toward expansion or collapse, to hold the cosmos in a kind of perfect, poised equilibrium. He called it the cosmological constant. It acted as a kind of pressure built into the fabric of space itself, a gentle, uniform outward push that balanced gravity's inward pull and allowed a static universe to exist as a mathematical solution. It was, in retrospect, a strange thing to do. Einstein himself was not entirely comfortable with it. The constant had no physical motivation beyond the desire for a static result. It was inserted by hand as a mathematical convenience, not derived from any deeper principle. But it worked in the narrow sense that it produced the equations for a universe that was neither expanding nor collapsing. Then, in 1929, Edwin Hubble published observations of distant galaxies showing that they were moving away from us, and that the farther away a galaxy was, the faster it was receding. The universe was not static. It was expanding. Had been expanding all along. Einstein's equations without the cosmological constant had been right the first time. The constant had been unnecessary. Einstein struck it from his equations and reportedly called it his greatest mistake. The story of a genius who briefly lost his nerve, patched his own beautiful theory with an ugly fix, and then had to admit the error. It became one of the most famous anecdotes in the history of physics. But here is where the story takes its long, patient turn. The cosmological constant didn't disappear. It sat in the back rooms of theoretical physics for decades, neither fully accepted nor entirely forgotten. Some researchers kept it around as an optional parameter, a dial that could be set to 0 if observations demanded it. Others played with the possibility that it might not be 0, that there might be some small but genuine energy associated with space itself. The equations permitted it. Whether nature chose to use it was another question. Then came 1998, and the supernovae and the accelerating universe. And suddenly, the cosmological constant was the most natural explanation anyone had for what was being observed. If you put it back into Einstein's equations, not set to the value Einstein had chosen, but set to a small positive value, the mathematics produced exactly the kind of accelerated expansion that Perlmutter, Schmidt, and Riess had measured. The constant that had been introduced to hold the universe still was now, it turned out, the simplest candidate for the force that was tearing it apart. The irony is layered and wonderful. Einstein's blunder, it turned out, was not the introduction of the cosmological constant. The blunder was abandoning it. The equations had been trying to tell him something, and he had silenced them because he didn't like the answer. What the cosmological constant means, physically, is this. Space has energy, not the energy of particles moving through it, not the energy of radiation crossing it, the energy of space itself, of the vacuum, simply by virtue of existing. Every cubic centimeter of empty space, according to this picture, carries a tiny fixed amount of energy. And as the universe expands and more space comes into being, that energy does not dilute. It persists, constant in density, a property of the fabric, rather than of anything within it. This is deeply unlike any other form of energy we know. When matter spreads out across a larger volume, its density falls. When radiation expands, it thins and cools. But the cosmological constant, if that is what dark energy is, maintains its density regardless of how much space there is. In the early universe, when everything was compressed into a tiny region, the cosmological constant's total contribution to the energy budget was negligible compared to the enormous density of matter and radiation. But as the universe expanded, matter and radiation thinned out, while the constant energy of space remained. Eventually, about 9 billion years after the Big Bang, the balance tipped and the vacuum energy began to dominate, pushing the expansion into acceleration. General relativity, in this reading, was never wrong. It described a universe that could contain a cosmological constant all along. Einstein's real error was a philosophical one, the assumption that the universe ought to be static, and that assumption led him to introduce the constant for the wrong reason, and then to discard it when the right reason was still half a century away from being discovered. The equations waited. They are patient things. Equations, they don't mind. Let's go somewhere quieter now, smaller, all the way down to the level where the strange behavior of empty space begins. The cosmological constant says that the vacuum, the void, the absence of everything has energy. That is a remarkable claim. And it turns out that modern physics, quite independently of cosmology, has reasons to believe it might be true. The reasons come from quantum mechanics, from the behavior of the very smallest things, and they lead to one of the most uncomfortable numbers in all of science. To understand why empty space might have energy, you first need to understand something about the quantum world. In the physics of very small things, atoms, electrons, photons, there is a principle that places a fundamental limit on how precisely you can know certain pairs of quantities at the same time. The position and momentum of a particle, for instance, cannot both be perfectly defined simultaneously. The more precisely you pin down where something is, the more uncertain its momentum becomes, and vice versa. This is not a limitation of our instruments. It is a feature of how nature actually works at the smallest scales. One consequence of this, and it is a consequence that has been tested and confirmed in laboratories to extraordinary precision, is that empty space cannot be truly, perfectly empty. If a region of space contained absolutely nothing, with every field at zero and every energy exactly defined, that would violate the uncertainty principle. So instead, the vacuum is restless. It seethes with what physicists call vacuum fluctuations, pairs of particles that flicker into existence for an instant and then annihilate each other and vanish, too brief to be detected directly, but real enough to leave measurable traces. These are sometimes called virtual particles, not because they are imaginary, but because they exist only within the window of time that the uncertainty principle permits before they must disappear. The effect of these fluctuations has been confirmed in a beautiful and precise experiment. If you take two uncharged metal plates and hold them very close together, a fraction of a millimeter apart, they are pulled toward each other by a tiny but real force. There is nothing between them. No air, no charge, no field in the conventional sense. Yet they attract. The reason is that the space between the plates can only support vacuum fluctuations with wavelengths small enough to fit in the gap, while the space outside can support fluctuations of all wavelengths. This creates a slight pressure difference, and the plates are pushed together by the imbalance. This is called the Casimir effect, after the Dutch physicist Hendrik Casimir, who predicted it in 1948, and it has been measured repeatedly. It is real. So the vacuum has energy. Quantum mechanics insists on it, and experiments confirm it. The question for cosmology is, how much? This is where the trouble begins. Physicists can calculate, using quantum field theory, the framework that describes particles as excitations of fundamental fields, the most precisely tested theory in the history of physics, what the energy density of the vacuum should be. The calculation involves adding up the contributions from all the quantum fluctuations of all the known fields up to the energy scales where we trust our theories. The answer, depending on how you do the calculation and where you set the cutoff, comes out somewhere around 10 to the power of 110 times larger than the value of dark energy that astronomers have actually measured. 10 to the power of 120. Write out a 1 and then write 120 zeros after it. That is the factor by which the theoretical prediction overshoots the observation. There is no other number in physics, in any branch of science, in any comparison between theory and measurement, that comes even remotely close to being this wrong. It is sometimes called the worst prediction in the history of physics, and that description is not an exaggeration. The theory and the observation disagree by more than any two numbers in science have ever disagreed. And yet both the theory and the observation are solid. Quantum field theory is not a speculative framework. It predicts the magnetic properties of the electron to more than 10 significant figures of accuracy, the most precise prediction ever confirmed in science. The measurement of dark energy's density is not a rough estimate. It has been refined by decades of observation from multiple independent methods. Both numbers are as reliable as numbers in physics get, and they are separated by a factor of 10 to the power of 1030. What this tells us is that something is missing. There must be some mechanism, some cancellation, some symmetry, some principle we have not yet discovered. That takes the enormous raw vacuum energy that quantum mechanics generates and reduces it, almost, but not quite to zero, leaving behind the tiny residual that we observe as dark energy. The precision required for this cancellation is extraordinary. Imagine adjusting a dial that runs from 0 to a number with 120 digits and needing to set it with enough accuracy that the remaining value is correct to within one part in that same vast number. Some mechanism in the universe appears to be doing exactly that, and we have no idea what it is. Some physicists have proposed a symmetry called supersymmetry, a deep mathematical relationship between the two broad families of particles, which in principle would cause the vacuum energy contributions from different particle types to cancel each other out. If supersymmetry were perfect, the cancellation would be complete, and the vacuum energy would be exactly zero. But we observe a small non-zero value. So if supersymmetry is relevant at all, it must be a broken symmetry, one that almost cancels, but not quite. Experiments at the Large Hadron Collider have so far not found the particles that supersymmetry predicts, which has made this explanation harder to sustain in its simplest forms, though the idea has not been abandoned. Others have suggested that what we call the cosmological constant is not actually the vacuum energy of quantum field theory at all, that the two quantities happen to be similar in magnitude purely by coincidence, and that dark energy has some other, entirely separate origin. But coincidences of this magnitude are hard to accept without explanation. What sits at the center of all this, quietly, is the gap itself. A gap of 10 to the power of 120 between what our best theory predicts and what the universe actually does. Dark energy lives in that gap. It is the measured residual of something we cannot yet explain. And it is the dominant component of the universe, more than 2/3 of all the energy that exists. There is something almost restful in that, if you let it settle. The largest mystery in physics is not hiding somewhere exotic or extreme. It is everywhere. It is in the space between your hands, between the atoms in the air around you, in every empty region of every room, in every building on Earth. The vacuum is not nothing. Or it never was. For most of the universe's history, dark energy was losing. Not absent, present, perhaps, even then, woven into the fabric of space, but overwhelmed, drowned out, irrelevant. Gravity was in charge, and gravity, given enough time and enough matter, does extraordinary things. Go back to the beginning, not all the way back. The first fractions of a second after the Big Bang are a separate story and a deeply strange one, but to perhaps a few 100,000 years in, the universe at that point was a dense, hot fog of particles and radiation, everything packed together, everything interacting. It was not yet transparent. Light could not travel freely. It was constantly scattered by the charged particles around it. And then, as the universe expanded and cooled, something settled. Temperature dropped to the point where electrons could bind to protons and form neutral hydrogen atoms. The fog cleared. Light streamed freely for the first time. And the universe became, in a sense, visible. What it looked like, in those first moments of transparency, was almost perfectly smooth. The temperature of the radiation left over from that epoch What we now observe as the cosmic microwave background, the faint afterglow of the Big Bang that fills the sky in every direction, was uniform to about 1 part in 100,000. The density of matter was nearly identical everywhere, nearly, but not quite. There were tiny fluctuations, ripples in the density of the primordial gas, some regions fractionally denser than others. Those tiny fluctuations were the seeds of everything. Gravity is democratic in the sense that it acts on all matter, but it is also, in the long run, deeply biased toward concentration. A region that is slightly denser than its surroundings exerts a slightly stronger gravitational pull on the material nearby. That material drifts inward. The region becomes denser still. Its pull grows stronger. More material falls in. The process is self-reinforcing, and over hundreds of millions of years, it transforms those tiny ripples in the primordial gas into something magnificent. The first stars formed roughly 100 to 200 million years after the Big Bang. Massive, brilliant, burning through their hydrogen at a ferocious rate, living fast and dying in spectacular explosions that scattered heavier elements, carbon, oxygen, iron, across the surrounding gas. Those elements, forged in stellar cores, became the raw material for the next generation of stars and for planets, and eventually for the chemistry of life. Meanwhile, on larger scales, the gravitational gathering continued. Stars clustered into galaxies. Galaxies were themselves drawn together by gravity, forming groups and clusters. And on the very largest scales, hundreds of millions of light years across, the distribution of matter in the universe took on a structure that astronomers describe as the cosmic web. Vast sheets and filaments of galaxies threaded through with enormous empty voids, the whole thing resembling, in cross-section, a foam or a sponge, or perhaps the interior of a sponge that has been stretched and thinned until its walls are made of galaxies, instead of soap. All of this was gravity's work, and during this entire epoch, from the Big Bang through the formation of the first stars, through the build-up of galaxies, through the first 9 billion years of cosmic history, the expansion of space was genuinely slowing down. Gravity was winning. The mutual attraction of all that matter was applying a brake to the expansion, just as everyone had assumed before 1998. The universe was decelerating. Now, to understand why dark energy eventually took over, you need to think carefully about what happens to density as space expands. Matter, ordinary matter, the stuff of stars and gas and planets, has a fixed mass. As the universe expands and the volume of space increases, that mass is spread across a larger region. The density of matter falls. Double the volume, halve the density. This relationship is straightforward and inexorable. Dark energy, if it behaves like the cosmological constant, does not follow this rule. Its energy density is a property of space itself, not of anything within space. When the universe expands and new space comes into being, the energy density of the vacuum stays the same. Every cubic centimeter of new space arrives with the same energy density as every existing cubic centimeter. The total amount of dark energy grows as the universe grows, but its density per unit volume never changes. This difference in behavior is everything. In the early universe, matter was packed densely enough that its gravitational influence utterly dominated the cosmological constant's gentle push. The ratio was not close. Matter was far denser, far more gravitationally influential, and the constant was a negligible footnote in the energy budget. But as billions of years passed and the universe expanded, matter thinned, its density fell. The constant stayed put. The ratio shifted slowly across 9 billion years until roughly 5 billion years ago, when the universe was about 2/3 of its current age. And then, as expansion continued, matter thinned further while dark energy held steady and the balance tipped decisively. The mechanism of the transition is worth pausing on because it is genuinely subtle. Gravity's ability to decelerate the expansion depends on the total energy density of the universe and also on the pressure within it. In general relativity, pressure contributes to gravity, not just mass. Ordinary matter has effectively zero pressure on cosmological scales. Gas and stars exert pressure locally, but spread across the vastness of space, the average pressure of matter is negligible. Radiation has positive pressure, which adds to its gravitational effect. Dark energy, however, has negative pressure. This is the key. Whatever dark energy is, its pressure is negative, meaning it does not push inward the way ordinary pressure does, but outward. And in the equations of general relativity, a sufficiently negative pressure creates not gravitational attraction, but gravitational repulsion. It is not that dark energy switches off gravity, it is that dark energy's negative pressure contributes to the geometry of space in a way that drives expansion rather than resisting it. When matter was dense enough, its positive gravitational influence overwhelmed dark energy's negative pressure, and the universe decelerated. As matter thinned, the balance shifted. Around 9 billion years after the Big Bang, dark energy's repulsive effect crossed the threshold and began to dominate. The deceleration slowed, halted, and reversed. The universe began to accelerate. From that moment, 5 billion years ago, give or take, the cosmos has looked different. Structures that were still in the process of collapsing under gravity found their growth slowed and eventually halted. The cosmic web stopped gaining detail at the very largest scales. Galaxies that had been drifting together began to drift apart again. And the expansion, once braked by gravity, became a runaway, not fast enough on human timescales to notice, but relentless across cosmic time, pulling the observable universe apart in ways that will, in the very long run, leave each galaxy island alone in an otherwise empty dark. What strikes me, thinking about this, and you don't need to think about it, just let it drift past, is how patient the process is. And only then, when the work was largely done, did dark energy step forward and begin to undo it, slowly, unhurried, as if it had been waiting all along. To measure something you cannot see, you have to be very clever about what you can see. Dark energy leaves no direct trace, no particle, no radiation, no field you can point an instrument at. What it leaves is a shape, the shape of the universe's expansion over time. And reading that shape requires some of the most ingenious techniques in all of observational science. The story of how astronomers measured dark energy is really a story about light, about what happens to light as it travels across an expanding universe, and about the extraordinary precision with which we have learned to interpret its signals. Begin with the Type Ia supernovae we met in the first chapter. We know they are standard candles, all exploding at very nearly the same intrinsic brightness, because they all detonate when a white dwarf crosses the same mass threshold. But the real situation is slightly more nuanced, and the way astronomers handle that nuance is a beautiful piece of detective work. In practice, Type Ia supernovae are not perfectly identical. There is a small spread in their peak luminosities. But in the early 1990s, an astronomer named Mark Phillips noticed something remarkable. The brightness of a Type Ia supernova is correlated with how quickly it fades. Supernovae that are intrinsically brighter at their peak also fade more slowly over the following weeks. Supernovae that are fainter fade more quickly. This relationship, sometimes called the Phillips relation, or the width-luminosity relation, means that by watching how a supernova's brightness evolves over time, you can correct for the variation and pin down its true peak luminosity with much greater precision. Once you know the true luminosity, the observed brightness tells you the distance. The standard candle becomes, in effect, a calibrated one. The light from these distant explosions is also stretched by the expansion of space. A supernova that detonated 7 billion years ago emitted light at a particular set of wavelengths, characteristic signatures of silicon, calcium, and other elements in the explosion. By the time that light reaches our telescopes, the universe has expanded, and every wavelength has been stretched proportionally. What began as a particular color of ultraviolet or visible light arrives redshifted, displaced toward longer wavelengths, toward the red and infrared end of the spectrum. By measuring how much the light has been stretched, astronomers can determine the redshift, which tells them how much the universe has expanded since the supernova exploded. Combine that with the distance derived from the brightness, and you have a data point that places you at a specific moment in the universe's expansion history. Accumulate hundreds of such data points across a range of distances and redshifts, and the shape of the expansion history emerges. This is what Perlmutter's team and Schmidt and Rees's team were doing. And this is what modern supernova surveys continue to do, with far greater numbers of events and far more precise instruments. But Type Ia supernovae are not the only ruler astronomers have. There is another method, quite different in its origin, called baryon acoustic oscillations. And to understand it, you need to go back to the very early universe, to that hot, dense fog of particles and radiation we visited in the last chapter. In the first few 100,000 years after the Big Bang, the universe was filled with a tightly coupled mixture of ordinary matter, baryons, meaning protons and neutrons, and the atoms they form, and radiation, meaning photons. A slight overdensity of matter would create a pressure pulse that radiated outward through the hot plasma, carrying matter and radiation together in a spherical shell expanding at slightly more than half the speed of light. When the universe cooled enough for atoms to form, that moment of clearing we described earlier, the radiation decoupled from the matter and streamed away freely. The pressure wave froze. The shell of slightly enhanced matter density stopped moving and remained imprinted on the distribution of galaxies like a ring frozen in time. This ring has a characteristic size, about 490 million light-years across, in today's universe, and because it was set by the physics of that early epoch, which we understand very well, it serves as a known length scale, a cosmic ruler. When astronomers map the distribution of galaxies across the sky, they can detect this preferred scale in the statistics of how galaxies cluster. Galaxies are slightly more likely to be separated by this characteristic distance than by slightly larger or smaller distances. It is a subtle signal, spread across the entire sky, but detectable with enough galaxies. By measuring the apparent size of this ruler at different epochs, that is, at different redshifts, astronomers can trace how the universe's expansion has changed over time, and thus measure the influence of dark energy across cosmic history. The dark energy spectroscopic instrument, known as DESI, is the most powerful machine ever built for this purpose. It sits at the Kitt Peak National Observatory in the Sonoran Desert of Arizona, mounted on the 4-meter Mayall telescope, and it is a genuinely extraordinary piece of engineering. Its focal plane, the surface at the top of the telescope where light from the sky comes to focus, is covered with 5,000 tiny robotic positioners, each one capable of moving independently to place a small optical fiber precisely on the image of a specific galaxy. Each fiber carries the light from its galaxy down to a spectrograph, an instrument that spreads the light into its component wavelengths and records the spectrum. From the spectrum, the redshift can be measured. On a good night, DESI measures the redshift of about 100,000 galaxies. It began its main survey in 2021 and is expected to measure the positions and redshifts of more than 30 million galaxies over 5 years. In Chile, at the Cerro Tololo Inter-American Observatory high in the Atacama Desert, there is another instrument, the Dark Energy Camera, mounted on the 4-meter Blanco telescope. It is a 570 megapixel digital camera, one of the largest astronomical cameras ever built, capable of imaging enormous swaths of the southern sky in a single exposure. The Dark Energy Survey used this camera over 6 years, from 2013 to 2019, to photograph 669 million galaxies, measuring their shapes, positions, and brightnesses. From those images, the survey extracted not just galaxy positions, but the subtle distortions in galaxy shapes caused by gravitational lensing. Gravitational lensing is the bending of light by mass. General relativity tells us that mass curves space, and curved space bends the paths of light rays passing through it. When light from a distant galaxy travels toward us through regions of space containing other galaxies or clusters of galaxies, the mass of those intervening structures bends the light slightly, distorting the image of the background galaxy. The distortion is usually tiny, a slight stretching of the galaxy's apparent shape, a few percent at most. But when you measure millions of galaxy shapes and look for coherent patterns in how they are distorted, you can map the distribution of mass between us and them. This technique is called weak gravitational lensing. Weak because the distortions are small and statistical, as opposed to the dramatic arcs and multiple images of strong lensing, where a very massive object creates spectacular distortions of background sources. Weak lensing is extraordinarily powerful, because it responds to all mass, including dark matter, which makes up most of the universe's matter, but emits no light of its own. And, crucially, the pattern of lensing distortions across the sky encodes information about how matter has clumped together over cosmic time, which in turn depends on the balance between gravity, which encourages clumping, and dark energy, which suppresses it by driving matter apart. What the data actually looks like before any interpretation is worth pausing to imagine. In the case of galaxy surveys, it is a catalogue, a list of positions, redshifts, and brightness measurements for tens of millions of objects, each one a galaxy containing hundreds of billions of stars, each one billions of light years away. The raw data files are enormous. The processing, correcting for the atmosphere's blurring effects, removing contamination from nearby stars, calibrating the instruments, accounting for systematic biases, takes months of computation. And then, from that processed catalogue, statistical patterns are extracted, the baryon acoustic oscillation peak in the two-point correlation function of galaxy positions, the power spectrum of lensing distortions, the abundance of galaxy clusters as a function of redshift. These are the fingerprints of dark energy, indirect, subtle, requiring vast datasets and careful analysis to detect, but real, and growing more precise with every passing year as new instruments come online and new surveys begin their long, patient accumulation of data. The simplest version of dark energy is a fixed quantity, a constant energy density woven permanently into the fabric of space, the same everywhere, the same always, never varying by so much as a fraction across the entire history of the universe. This is what the cosmological constant describes. It is elegant in its simplicity. It fits the data, at least to the precision of most observations, and it is, many cosmologists would admit, a little unsatisfying, not because elegance is a scientific criterion, but because a truly constant, perfectly uniform energy density with no explanation for its value raises questions that feel important and that nobody has answered. What if dark energy is not constant? What if it is a thing that evolves, that had a different density in the past, that will have a different density in the future, that is not a fixed property of space, but a dynamic field pervading it? This possibility has a name, drawn from ancient philosophy. It is called quintessence, meaning a fifth essence, the four classical elements of earth, water, fire, and air, and then something beyond them, a fifth ingredient that fills the cosmos and is unlike anything else. To understand what a field means in this context, let's be precise, because the word is used in a specific way in physics. A field is not a region or an area. It is a quantity that has a value at every point in space, and that value can vary from place to place and change over time. Temperature is a familiar example of a field. At every location in a room, the temperature has a specific value, and that value changes across the room and changes over time as the heating comes on or a window is opened. The electromagnetic field is another example. At every point in space, there is an electric field value and a magnetic field value, and these values change as charges move and currents flow. Fields are the basic language of modern physics. Every fundamental particle is, in the framework of quantum field theory, an excitation, a ripple, in an underlying field that permeates all of space. Quintessence proposes that dark energy is a field of this kind. Call it a scalar field, meaning it has just a single value at each point in space rather than a direction as well. This scalar field would have energy associated with it, and that energy would act as a source of the repulsive pressure we observe. But unlike the cosmological constant, the field's energy density would not be fixed. It would evolve as the universe ages, rolling slowly through a landscape of possible values, its behavior determined by a potential energy function, a kind of mathematical terrain that describes how the field's energy changes with its value. Here is the crucial difference in behavior. If quintessence is a dynamic field, then its energy density in the past was different from what it is today, and its density in the future will be different again. The cosmological constant, by contrast, never changes. This means the two scenarios make different predictions about the history of the universe's expansion, and those different predictions are, in principle, distinguishable with precise enough measurements. Cosmologists parameterize this difference using a quantity called the equation of state of dark energy, often denoted by the letter W. This parameter describes the relationship between dark energy's pressure and its energy density. For the cosmological constant, this ratio is exactly negative, 1, always, everywhere, forever. For quintessence, the ratio can differ from -1, and crucially, it can change over time. If W is measured to be different from -1, or if it is found to evolve, then dark energy is not the cosmological constant and something more interesting and more complex. For most of the years since 1998, measurements of W have been consistent with -1. The cosmological constant has remained the simplest explanation that fits the data. But in early 2025, something changed. The Dark Energy Spectroscopic Instrument released results from its first 3 years of observations, covering millions of galaxies and incorporating baryon acoustic oscillation measurements of extraordinary precision. When the DEEC collaboration analyzed their data in combination with other cosmological datasets, measurements of the cosmic microwave background and of Type Ia supernovae, they found a hint that dark energy's density may not be constant. The data showed what appeared to be a slight evolution in the equation of state, a suggestion that W was not sitting precisely at -1, but was shifting. The statistical significance of the finding ranged from roughly 3 to 4 standard deviations. In physics, a 4 sigma result means there is about 1 chance in 15,000 that the deviation arose by random chance. That is not yet the 5 sigma threshold conventionally required to declare a discovery, but it is far from negligible. What the DESE data specifically suggested was that dark energy may have been slightly more energetic in the past and is slowly decreasing in density now. If true, this would rule out the cosmological constant as the explanation, because a cosmological constant cannot decrease. It would point toward quintessence, or something like it, a dynamic field that is rolling slowly through its potential, losing energy as it goes. The implications of this, if it holds up, would be profound. A dynamic, dark energy field is a new fundamental ingredient in the universe, with properties, a mass, a coupling to other fields, a potential energy function. That would need to be understood. It would mean the universe's expansion history is more complex than the simple accelerating growth the cosmological constant predicts. And it would mean the universe's future is less certain. A dark energy that is decreasing might continue to decrease, might eventually reverse, might even change sign and become attractive rather than repulsive. At the same time, the final results from the Dark Energy Survey, released in 2026 and covering 669 million galaxies, largely aligned with the standard cosmological constant picture. The two datasets do not flatly contradict each other. They are measuring somewhat different things in somewhat different ways, but the tension between them is real, and the community is watching carefully. More data is coming. The Vera Rubin Observatory in Chile, with its 3,200 megapixel camera, the largest digital camera ever built for optical astronomy, began operations in 2026 and will spend 10 years mapping billions of galaxies, providing the precision needed to resolve this question. NASA's Nancy Grace Roman Space Telescope, with a field of view 100 times larger than the Hubble Space Telescopes, will survey billions of galaxies and thousands of supernovae from space, free from the blurring effects of Earth's atmosphere. The question of whether dark energy changes is, right now, genuinely open. It is one of the most actively contested questions in observational cosmology, and the answer matters enormously, not just for our understanding of dark energy itself, but for everything that follows from it, the universe's past history, its present state, and its ultimate fate. There is something worth sitting with in the uncertainty itself. The data is not yet conclusive. The models are not yet settled. The universe has not yet told us which story it is telling. And in that gap between what we know and what we are still learning, there is a kind of honest, open wondering that feels, in its own way, like a form of peace. There is a question at the heart of dark energy that sits at the boundary between physics and philosophy, and it has no satisfying answer. It is not a question about mechanisms or measurements. It is a question about timing. Why now? More precisely, why are we living in the one cosmic era in which the density of dark energy and the density of matter are comparable? Not identical. Dark energy is currently about twice as dense in energy terms as all the matter in the universe combined, but the same order of magnitude. Given how differently the two quantities behave over time, this is not something you would expect by chance. Here is the problem in its full form. Matter's energy density scales with the inverse cube of the universe's size. Double the size of the universe, and matter's density falls by a factor of 8. Dark energy's density, if it is the cosmological constant, does not change at all. In the early universe, matter was enormously denser than dark energy. The ratio was perhaps 10 to the power of 90 to 1 in the very early moments. In the far future, matter will be so thinned out that it will be negligible, and dark energy will utterly dominate. Only in a very narrow window of cosmic history, a window that happens to contain right now, the present moment, the era in which we exist, are the two densities close to comparable. This is called the cosmic coincidence problem. It is the question of why, given the vast sweep of cosmic time, we find ourselves in the one epoch where both matter and dark energy are significant players rather than one completely overwhelming the other. If you were to pick a random moment in the universe's history, from the Big Bang to the indefinitely far future, the odds of landing in an era where matter and dark energy are within a factor of a few of each other are extraordinarily small. Yet here we are. One response to this is to say, so what? We can only exist in an era where conditions are right for our existence, and that includes an era where matter is dense enough to have formed galaxies and stars and planets. Galaxies require a certain density of matter to form. If dark energy had become dominant much earlier, If the cosmological constant had been even slightly larger, the gentle overdensities in the primordial gas would never have had time to collapse under gravity before dark energy drove everything apart. There would be no galaxies, no stars, no planets, no us. The fact that we are here to observe the universe selects, automatically, for an era in which conditions were compatible with our existence. This style of reasoning is called anthropic reasoning, from the Greek word for human, and it says, in essence, that our very existence as observers constrains which part of the universe's history we can observe. Anthropic reasoning is not universally beloved among physicists. Many find it philosophically unsatisfying because it does not explain anything in the traditional scientific sense. It does not derive the value of the cosmological constant from first principles or predict it from a deeper theory. It simply says that we are here because we could only be here in an era like this one. It is a selection effect, not an explanation. But anthropic reasoning becomes more compelling, or at least more structured, in the context of a broader framework, the multiverse. The idea here is that our observable universe, the region of space we can in principle see, is not the whole of existence. If inflation, the period of extraordinarily rapid expansion in the universe's first tiny fraction of a second, produced an enormous, perhaps infinite, collection of separate regions of space, each with different values of the fundamental constants, then the cosmological constant would have different values in different regions. Most regions would have a cosmological constant so large that they would expand too quickly for galaxies to form. A very small fraction would have a cosmological constant small enough to permit structure, and in those rare regions, by the anthropic principle, observers would arise and would measure a small cosmological constant. Our universe might simply be one of the lucky ones. This idea was made more precise by the physicist Steven Weinberg in 1987, more than a decade before dark energy was discovered. He used anthropic reasoning within a multiverse framework to predict that the cosmological constant, if it existed, should be small, but non-zero, large enough to be measurable, but not so large as to prevent galaxy formation. When the accelerating expansion was discovered in 1998, Weinberg's prediction was cited as one of the few prior theoretical arguments that had anticipated a non-zero cosmological constant. It was a striking success for an approach that many physicists still find uncomfortable. The discomfort is real and legitimate. The multiverse is not currently testable in any direct way. We cannot observe other regions of the multiverse by definition. They are beyond any possible horizon, separated from us by distances that no signal can ever cross. A theory that explains our observations by appealing to an enormous collection of unobservable universes is, to many scientists, uncomfortably close to not being a scientific theory at all. There are other approaches. Some physicists have proposed modified gravity theories, frameworks in which Einstein's general relativity is not wrong exactly, but incomplete, and in which corrections to it at very large scales produce effects that mimic dark energy without requiring any new form of energy at all. In these theories, the accelerating expansion is not driven by a mysterious substance, but by the behavior of gravity itself when applied to the cosmos as a whole. The challenge for these theories is that general relativity has been tested with extraordinary precision in the solar system, in binary pulsars, in the gravitational wave signals from merging black holes, and it has passed every test. Any modification must leave those successes intact while producing different behavior only at the very largest scales. This is a tight constraint, and no modified gravity theory has yet achieved the combination of theoretical consistency and observational agreement that would displace general relativity as the standard account. And then there is a deeper version of the coincidence problem that goes beyond the ratio of densities. The value of the cosmological constant itself, not relative to matter density, but in absolute terms, is astonishingly small. It is, as we explored in the previous chapter, about 10 to the power of 120 times smaller than the naive quantum field theory prediction. Why is it so small? Why is it not zero? Why is it precisely the value needed to cause the universe to begin accelerating just as complex life was emerging? These three questions may have the same answer, or they may have three different answers, or none of them may have answers that we are capable of understanding with our current mathematical frameworks. What the cosmic coincidence problem ultimately illuminates is the limits of our understanding. We have a precise measurement, dark energy's density, and we have no convincing explanation for why that number has the value it does. We have a timing. Dark energy became dominant roughly 9 billion years after the Big Bang, just as the universe's matter had thinned enough to permit it, and we have no fundamental reason why that timing should coincide with the emergence of life capable of noticing it. It may be a selection effect, inevitable given our existence. It may be telling us something about the multiverse, or about the nature of time, or about some symmetry in physics that we have not yet discovered. Or it may simply be the universe being the universe, vast, ancient, indifferent to our categories, and quietly, endlessly surprising. The universe tonight is vast and still expanding, not visibly, not in any way you could notice from here. The distances are too large, the motion too slow on human timescales. But if you could watch the cosmos from outside, if you could see the whole of it laid out across time as well as space, you would see the galaxies moving apart with a gentle, quickening persistence. Clusters of galaxies bound to each other by their mutual gravity will stay together. Gravity at short ranges still wins, but the space between those clusters is growing and growing faster and will go on growing for longer than any number we have words for. What happens next depends on what dark energy turns out to be, and the three main possibilities paint three different futures, each one vast and quiet in its own way. The first future belongs to the cosmological constant. If dark energy is truly a fixed, unchanging property of space, the same density now as it was 9 billion years ago, and the same as it will be 9 billion years from now, then the universe expands forever. Not at a constant rate, but at an accelerating one. The expansion grows faster over time, driven by the ever-increasing total amount of vacuum energy as more and more space comes into being. Galaxies beyond our local cluster, the small collection of galaxies, including the Milky Way and the Andromeda Galaxy and a few dozen smaller companions that are gravitationally bound together, will drift away from us. Their light will be stretched by the expansion until it is redshifted beyond any detector we could build. Eventually, in a time scale of roughly 100 billion years, several times the current age of the universe, the last galaxies will cross what cosmologists call the cosmic event horizon, a boundary beyond which the space between us and them is expanding faster than light can cross it. Not because anything is moving faster than light, nothing is, but because the space itself is growing faster than light can traverse it. Those galaxies will vanish from our observable universe, and the night sky will grow darker and emptier. The stars in our own galaxy will continue to burn. The most massive stars live only millions of years, but the most frugal, the small, dim red dwarf stars that make up the majority of stars in the Milky Way, will burn for trillions of years, fusing hydrogen into helium with extraordinary patience. Over a timescale of about 10 trillion years, the last of these dim embers will exhaust their fuel and fade. No new stars will form because the gas needed to form them will have been used up. The galaxy will grow dark, populated by the cooling remnants of dead stars. White dwarfs fading toward black, neutron stars, black holes, drifting apart in an increasingly empty space. Over timescales that dwarf even this, timescales so long that the numbers are essentially meaningless to human intuition, even the stable remnants will change. Protons, if they are not perfectly stable, may decay over timescales of perhaps 10 to the power of 40 years, dissolving the last atoms into lighter particles and radiation. black holes, through a process of slow quantum evaporation called Hawking radiation. The gradual emission of energy by a black hole due to quantum effects near its edge will eventually evaporate over timescales ranging from millions to 10 to the power of 67 years for the largest ones. And then, when all of that is done, what remains is an extraordinarily sparse, cold, featureless expanse of space populated by the lowest energy particles, photons of almost zero energy, neutrinos, perhaps the occasional positron or electron, drifting apart forever in a universe that has reached its maximum entropy. It is not a violent end. It is a slow dimming, a patient cooling, a universe that simply runs down and rests. There is something in that image that feels, to me, not desolate, but almost peaceful. A universe that has done everything it was going to do and is now simply being. The second future belongs to a different kind of dark energy, one that does not stay constant, but grows stronger over time. If the energy density of dark energy increases as the universe expands, rather than remaining fixed, then the repulsive force it exerts becomes progressively more powerful. At first, the effect is similar to the cosmological constant scenario. Galaxies drift apart, structures thin, but as dark energy strengthens, the repulsion eventually grows large enough to overcome not just the gravity between galaxies, but the gravity holding individual galaxies together. Then the repulsion grows strong enough to unbind star systems, to push the planets away from their stars. Then it grows strong enough to overcome the forces holding the star itself together. Then the electromagnetic forces holding atoms together. Then, in the final moments, the strong nuclear force binding protons and neutrons in atomic nuclei. Everything, every structure, every bond, every particle arrangement is torn apart in a finite time in what is called the Big Rip. The timing of the Big Rip, if it occurs, depends on the precise way dark energy strengthens over time. For some models, it would happen in roughly 20 billion years from now. For others, much longer. In the final moments before the rip, in the last minutes of cosmic time, even the nuclei of atoms would be shredded, and space itself would be tearing apart on the smallest scales. It is a more violent ending than the Big Freeze, but it is also, in a sense, a quicker one. The universe would not linger through those unimaginable timescales of slow cooling. It would end decisively. The third future is the most uncertain and perhaps the most interesting because it is the one the DESI data from 2025 hints at. If dark energy's density is decreasing over time, if the DEESI results hold up and are confirmed by future surveys, then the future of the universe is genuinely open in a way it has not been before. A decreasing dark energy might simply slow the acceleration. The universe would still expand, but less frantically, and structures might have more time to form and evolve. Or the decrease might continue until dark energy's density approaches zero, at which point gravity would once again dominate and the expansion might slow to a halt. And if dark energy's density were to cross zero and become negative, if whatever dynamic field is responsible were to reverse its sign, then gravity would take over entirely, and the expansion would reverse. The universe would begin to contract, slowly at first, then faster, the galaxies rushing back toward each other, the temperature rising, the density increasing, until everything collapsed back into a state as hot and dense as the Big Bang. Cosmologists call this the Big Crunch. The Big Crunch is not favored by the current data. The universe is expanding too vigorously right now for a reversal to be imminent, but it is not ruled out if dark energy's behavior is sufficiently dynamic. Some theorists have speculated that a Big Crunch might be followed by another Big Bang, a cycle of expansion and collapse that has been repeating indefinitely. This is called a cyclic cosmology, and it is a minority view, but it is a view that the equations do not prohibit. Each of these futures is a kind of landscape, vast, quiet, beyond the scale of anything human. The Big Freeze, with its patient dimming across trillions of years. The Big Rip, with its decisive and final unraveling. The Big Crunch, with its compression back into fire and possibility. None of them need to frighten us, because they are so far beyond the scope of any human concern that they exist in a different category of reality from our lives. They are the universe's futures, not ours. We are here now, in this brief and extraordinary window. A window that required 9 billion years of preparation, of stars living and dying and scattering their elements, of planets cooling and chemistry complexifying and life finding its way towards something that could look up and ask questions. That is the thing worth holding on to as the night deepens around you. We are the universe looking at itself, not a phrase to be said quickly and passed over, but one to let sit for a moment. The hydrogen in your body was forged in the Big Bang. The carbon in your cells was made in the cores of stars that died before the sun existed. The iron in your blood was scattered by supernovae, the same kind of stellar explosions that Perlmutter and Schmidt and Rius used to discover that the universe is accelerating. You are made of the same stuff as the cosmos, and you are, right now, the part of the cosmos that is aware of dark energy, that has measured it and named it and sat quietly wondering what it is. Dark energy makes up 68% of everything. It fills every corner of space, including the space of this room, including the air around you, including the gaps between atoms in the pillow beneath your head. It is there, gently and persistently present, doing what it has been doing for billions of years, pushing space apart, unhurriedly, across distances that make the whole of human history look like a single breath. And we still don't know what it is. We have its fingerprints in the brightness of ancient supernovae, in the distribution of galaxies across the sky, in the acoustic ring frozen into the cosmic web. We have its effects. We have its density, measured now to a few % precision. But its nature, its origin, the reason its value is what it is, these remain open, and genuinely open, in the way that the best scientific questions always are, not open because we haven't looked, but open because the universe is deeper than our current tools can reach. Maybe that is enough for tonight, to know that the question exists, to know that it is being asked, carefully and patiently, by people pointing instruments at the sky in the desert mountains of Arizona and Chile, accumulating photon by photon the light of galaxies so distant that the universe was young when that light began its journey. To know that the answer, when it comes, will change everything, and that it has not come yet, which means the mystery is still alive, still open, still worth wondering about. The universe is 13.8 billion years old. It has been expanding for all of that time and accelerating for the last 5 billion years, and it will go on, in one form or another, toward one of those vast and quiet futures for longer than any number we can name. And somewhere in the middle of all of that, on a small rocky planet orbiting an unremarkable star in the outer arm of one of hundreds of billions of galaxies, for a brief and improbable and deeply strange interval, there was life, there was awareness. There was the capacity to look up at the dark and ask, what is out there, and why is it doing what it is doing? You are part of that asking, even now, drifting towards sleep, with the questions only half formed and the answers nowhere near. You are part of the long, patient human project of trying to understand something so much larger than ourselves that the trying itself feels like a kind of love. The day is behind you now. Whatever it held, it is already distant. The universe is vast and old and still becoming, and tonight there is nothing required of you except this, to rest, to drift, to let the dark be comfortable rather than heavy. The questions will still be there tomorrow. The mystery will still be open. The instruments on their desert mountains will still be turning, gathering light from galaxies that no one will ever visit, reading the shape of a force that no one has ever touched. And you can sleep now, softly, The universe has this